Designing databases, there's two different sets of terminologies. When we're coming up with our model, which is the design, we speak about entities and attributes. Entities are the objects that we're modeling, and attributes are their properties. When we talk about the implementation in a database system like MySQL, we then talk about tables and fields or columns. So our database model entities map to our tables, and our database model attributes map to the fields or the columns. First thing you would do is make a list of all the different data you want to capture. And so for a car business, I thought of selling cars, maybe used cars. You need to know the make and model of the car, the year it was manufactured, the miles on the car, color, prior owners, price, buyer name, buyer phone. So for each car in your system, that might be all of the information you want to capture. The model, GT3 could go with two different makes, right? So we're storing too much information in that field. We're storing both the make of the car and the model of the car. So if you want to find out just all of your Porsches or all of your Bentleys, it'd be really hard to do. With problem with prior owners, what would happen is we had a third prior owner. Right? One fix we could do is add another field, call it prior owner number 3. But then you could have a fourth prior owner, and you could go on and on and on. The buyer's name, down at the bottom there, you see Bouvier and then Marge Simpson. So what happened? What did she do at some point in time between the time she bought the first and the second car? Got married and changed her name, right? So in our database, it looks like this is two different people, but it's really the same person. And that means every time Marge bought a car, her name would go into this system again. And let's say at some point she changes her phone number or her address. That means you would have to go through and find all of the Marge Simpsons in this database. And you would have to change the phone number for every single one. And as you can see, we would still miss some because there was a point where she had a different last name. So imagine trying to manage a business where you have all of these problems. It's a true story. Where I taught this class, which covered database design, I had a student who was always late and always really frazzled and stressed out. Finally found out what was up. He worked for a company that had a database like this, and it was his job to maintain it. And they knew that they had to fix their database, and they didn't know how to do it, so they were sending him to the class to learn the correct way to design a database, so hopefully his job would become easier in the future. The task we're going to perform now is called normalization. We're going to fix this database so that we don't have any of those problems we just discussed. First thing you do is you make sure that you have a primary key for your database. This is something that uniquely identifies your record. Sometimes things that look like they're a good unique key that could identify your subject might not necessarily be a good solution. Social security number is an example of that. Besides the privacy issues, and that not everybody really has one, if somebody suffers identity theft, they might be assigned a new social security number. Also, social security numbers are reused over time. So somebody could get a social security number that had been used by somebody else in the way past. So it's not really a good candidate for a private key because it doesn't really uniquely identify a record in a database. Commonly, what developers do is they'll make up an ID key or a surrogate key that is guaranteed to have a unique number within the database. Okay. Larry Ellman, when he wrote this book, said that each of the normal forms is defined in a very cryptic way, and even when put in layman's terms, they can still be confounding. We'll go through each one of those three normal forms step by step. So step 1, each attribute should contain only one value, and make sure that your entities do not have repeating groups of values. So in the example I created, which fields are storing more than one pieces of data? Make and model is the obvious one. So we would separate that out to two separate fields, a make field and a model field. What else? The buyer's name is actually consists of a first name and a last name. So we would want to break that out too. Sometimes it's hard to figure out if you should break something up or not. Phone numbers technically consist of an area code plus the rest of the number plus an extension. Most people will just usually leave the phone number as one field. And the reason is there are so many different formats for phone numbers. If somebody is out of the country, they will have a completely different format. Some people will have extensions, some people don't. So you could break it up if your application needed it, but it's not commonly done. The address will be broken down as well to the street address, city, state, zip. Whether or not you break down the street address depends on what you're doing. If you're just mailing out products to people, getting the street address in one field is fine, like 1 Memorial Drive. And then if there's a certain unit number, you could add that as well. If you're the post office, however, the post office breaks down that address line into every single specific field, the number, the street name, the unit name, because that level of detail is important for the type of application that the post office is writing. So your decision about whether or not you're going to be breaking down one field into smaller parts really depends on what your application needs to do. Where we have prior owner 1 and prior owner 2, that is a repeating field, so that's also part of the first normal form. We want to put that in a separate table. So the fix has the prior owners in a separate table, broken down to first name and last name. Our make and model are separate fields, and our buyer's name is now broken down into first name and last name. That's the easy one. Any questions about the first normal form? Okay. Now the second and third normal forms are about functional dependency. Definition for that is that the value of all of your attributes, that's everything listed under the primary key, should be determined by the primary key and only by the primary key. If I have the VIN number for a vehicle, the VIN number for a vehicle is unique. Only one car is going to have that VIN number. I can then determine all of the other attributes about the car, the make, the model, the prior owners. So all of those fields are functionally dependent on the VIN numbers. The second and third normal forms are about making sure that your attributes are functionally dependent on your private key. If you don't do that, if you have attributes that are not functionally dependent on the primary key or they're dependent on other things, that's where you start to get repeating redundant entries in the fields, like Marge Simpson's name appearing multiple times, and you have issues like the one where she changed her name, and you have update anomalies. If the primary key is a composite key, you want to make sure that the other attributes are functionally dependent on the entire composite key and not just a subset of the key. This is one I think that's conceptually harder to understand than some of the other normalization topics. For a deck of cards, now we can identify a unique card if we know the card's rank and the card's suit. Right? Does that make sense? So for example, there's only one 7 of spades in the deck. Right? If we know the number that's printed on the card, or the rank, because it might be a king or queen or jack. And if we know the suit, spades, hearts, diamonds, we can identify a specific card in that deck. So this is an example of a composite key, meaning our primary key is actually being made up of 2 different fields. Everyone with me so far? Good. Now the attribute that I put in this table is the point value. In card games, you can assign each card can get a certain number of points. So for example, the 7 would get 7 points. And the face cards like Jack, Queen, King, and King would get 10 points. So now, is point value functionally dependent on my primary key, card rank and card suit? So for example, if I know the rank and I know the suit, can I figure out how many points I would get for that card? Yes. But now, here's where the second normal form comes into play. Is the point value really functionally dependent on just a subset of that primary key? Right. So for example, if we know the card suit, can we figure out what the points are? So if we know it's a diamond or a spade, can we figure out the points? Right. The answer to that one is no. But if we know the rank, can we figure out what the point value is? The answer to that is yes. That the card rank is going to determine the number of points that somebody would get if they had that card. The 8 is always going to be worth 8 points. A 4 is going to be always worth 4 points. The rank of Jack is always going to be worth 10 points. So here the point value is technically functionally dependent on a subset of the composite key. It's very rare that people actually use composite keys. If you're familiar with MySQL, or if you've seen the examples in the book, what would they normally put as an extra field up the top? Well, yeah, technically card rank and card suit is a primary key. It's composite. But they would put another primary key. And what might you call that other primary key that you make up? Card ID, right? What they would also do is you'd put an index on card rank and card suit and make that unique to make sure you didn't get 2 7 of spades in the deck. People who are real database modelers might look at adding in the card ID. They might frown upon that because you're adding an extra field, it's taking up more storage space, and you're having to add an extra index. From a practical point, though, from people who actually do the programming, turns out MySQL and other database software don't really completely implement what relational databases are designed to do. So your queries are going to be a lot easier to write if you have the card ID field. And if we only have 52 cards, we're not exactly worried about running out of space. In the real world, you will generally see people throw up the card ID. Now, when you do that, when you have a card ID here, technically anything that has a primary key where you throw in a surrogate key like card ID is going to be in second normal form, because your primary key is now not a composite key. Your primary key is that new card ID that you created. I think that might be one thing that is confusing about the examples in the book. All of the examples that are written in the textbook that say they're violating second normal form technically are not violating the form, because all of those examples did have a surrogate primary key up top. Then he goes on and fixes those examples in the functional dependencies and then says, well, at this point, now your database is probably already in third normal form. Whereas what the author did was really fix the second normal form by throwing in a surrogate primary key and fixed a lot of the third normal form issues during that process. This illustrates that problem. We can see here there's a duplicate, queen, queen, 10, 10. So that is not in second normal form, and here's the fix to move the point value out and use the card rank as the primary key in the entity where we assign the point value. And we can still have our playing card entity where our rank and suit are the primary key, and we have other attributes here. Or we could add in that card ID as well, and that would work as well. Okay. So I just explained that slide. I will post these on SlideShare if anybody would like to download the presentation I'm giving you today. Okay. The third normal form states that attributes must be functionally dependent on the primary key and not on other attributes. So examples where we have problem of that, going back to my car database, the buyer's phone number. If we know the car ID, we know the ID of the car that gets sold. I mean, we could figure out what the buyer's phone number is, but technically the buyer's phone number doesn't depend on the car ID. What does the buyer's phone number depend on? The buyer, right? So the way to fix this and make it third normal form is to have a new table or a buyer's table where we could give it a buyer's ID, and we move in all that stuff, first name, last name, and phone number into that separate table. And then we would put that ID number in here as a foreign key, a buyer ID, which matches up with the other table that we've created that has the buyer in it. What other fields here might we have to fix to make it third normal form? Again, think about, we don't want to have any redundancies in the database, right? What would happen if we enter in a whole bunch of Porsches into our database and somebody spells it wrong, right? Misses an S by accident, or uses lowercase letters? We now have a bunch of entries that mean the same thing, right? So what you would do is you would probably want to have a separate table for your make too. where you give that a unique ID to make sure that there aren't multiple spellings or potential issues with that. So we would create a make table with the make ID and then the make name. And then you could type in the word Porsche once. And then anytime you wanted to refer to the Porsche, you would be able to follow the make ID in this table to our separate make ID database table. We'd want to do that also for model. We would not want to do that for year of manufacturer and miles. I put in 16,556 in both fields here. And while this is duplicated or redundant, it's not actually the normalization problem, right? It's just a coincidence that those cars have the same mileage. So the trick here is to figure out what's redundant, what's going to cause problems. If a bunch of cars have the same mileage or were manufactured in the same year, that's not going to cause confusion for our business. But if people enter in Porsche multiple times or different ways, that could cause a problem for our business. Yep. Color is one that might go both ways, right? If you want to be able to search for cars by color, you'd have to make sure the colors are entered exactly the same way every time. So you would probably want to add a color table. But you might also just want to have a free text field for accuracy, because paint colors are not necessarily marketed as white. They're marketed as things like aqua sky. It really depends on what your application needs to do. If it's a free text field, you would leave it. If it's a lookup, that's when you'd want to move it to a separate table.
Excuse me.
Yep.
Why wouldn't the date be in a separate table? Or
Question is, why wouldn't the date be in a separate table? Are those years something that you would need to look up in a separate table? Like, would you need to create a table that had a list of all possible years, like 2001, 2002, 2003? You actually might, right? If you know that certain makes and models only existed in certain years, you might want to make a table that has all the years that each car was manufactured and let people select from those years. If that's what you're thinking, then absolutely yes. If that's what your application needs to do, then you would have to put an ID there. Yep.
But there's no way to misspell a date.
Right, there's no way to misspell a date. You know, when you're doing the input, you filter the input so you make sure you have a valid year. You can use the functions that will make sure a valid year gets put into the database. Yeah, in that case, with your business, you have to, again, you always have to think about the application and what it's trying to do. If you just need a free text year field where people are typing in a valid year, you might not need to look up the year in a separate table. But if you have business logic where you want to constrain your makes and models to certain years, then yeah, that might be the solution. That might be the way you do that. In miles, it wouldn't make sense to do a lookup table. And that's a free text number. You wouldn't want to create a separate table that starts with car that has 1 mile, car that has 2 mile, right? That wouldn't help your business out in any way, so therefore you wouldn't do it. This decision is completely based on if it helps your business, if your application needs it. So you have to have the functional specs for your business, for your program. You need to know what the program needs to do in order to model your database correctly. Okay. So here is an example of that all broken out. We've got the make with its own ID, model with its own ID and name. The buyer is in a separate table, and now the owner is in a separate table. And you can see that all of these IDs in the make and model and buyer table are foreign keys in this other table. We have relationships between these tables. The way I would read this is if you have a car, the car can only have one possible make. However, a specific manufacturer could make many, many, many cars. So that's a one-to-many relationship. Same thing down here, car to buyer. The car on the lot can only be bought by one person. Then it's out of your business. Right? But that person could come back and buy more cars. Right? So again, that's a one-to-many relationship. We have a problem here between car and prior owners, because a prior owner can own many cars, but a car can also have many prior owners. And so we can't really write our queries in PHP and MySQL for this case. So one of the last tasks we have to do is find our tables that have many-to-many relationships and put in a table in the middle. We call that an intermediate entity. And here I put in the ownership entity is an intermediate entity between car and person. So now a person can buy a car, but also a person can own a car. So in this ownership table, it's a unique record in our database. So each line in this, each record in this table is going to refer to just one car and just one person. It represents one fact about a person who owned a car in the past. And now this has been turned into two one-to-many relationships, and you would then be able to do your queries with joins when you start writing your PHP. This is a database that is in third normal form. So a couple tips. We talk about second normal form and third normal form. It's not really that important to be able to identify which problem goes with which form. What's important to know is that you fix both types of functional dependency problems. If all of your functional dependency problems are fixed, then you'll be in third normal form, and that's where you need to get to. Another quote that I've heard in the past, you could call it the functional dependency pledge, is that when you're looking for these second and third normal form problems, you want to check every single one of your attributes and make sure that it provides a fact about the key, the whole key, remember not a subset of the key, and nothing but the key, meaning it's not dependent on something else. And then they add in so help me Cod. E.F. Cod was the inventor of relational databases. So a little cute quote that summarizes functional dependency. The last project I worked on, they set everything up, they ran it, and the query took like 15 seconds because they had millions and millions of records in this database. They were panicking. They're like, the whole system might be unusable if they can't get the time down to a fraction of a second. I came in, I added indexes on all the where clauses in all the queries they were using, in all the order by clauses they were using, and wherever their tables were joined together, what properties they were joined on. And the performance suddenly dropped to a fraction of a second where it should be, and I was the hero. And all I did was add in indexes to the databases. So this is a step you'll always want to do once you're implementing your databases. Delete anomalies is one I hadn't talked about yet, but just shows you something else that can go wrong. If you delete a record from one of those other tables you create, you could orphan keys in your other tables. As an example, look at the person table. If we were to delete a person, where would that person's ID still exist in our database? Yeah, the ownership table and also in the car table in the buyer field. So if we were going to look up historical records, you would try and find out who the buyer for the car is, and it would go to the person table to look it up, and that record wouldn't exist anymore. So you have a delete anomaly. So to fix this, have foreign key constraints. In other words, where a record has its primary key stored in other tables as foreign keys, you could do one of two things. Either don't allow the deletion to happen. So you can't delete that record because that information is needed somewhere else. Or you can cascade the delete, meaning not only would you delete that person record, but you would delete all of your car records that included the person, and you would delete all the ownership records that included that person. So depending on your business, you could do one of those two things. Deleting stuff from databases actually makes me really nervous. So the solution I use is to create an active field in my database. So I don't actually do deletes in my databases in PHP. My databases will either turn that active flag to Y or N. And if a field is inactive, I add that to my queries so it won't show up in queries. So to the end user, it will look like it's deleted. But if I ever need to get that information, I can just ignore the active flag because it's still in there. If their databases get too big and they really have to purge the records, might archive them. So there are other solutions besides deleting. Just one more note I wanted to make. Inner versus outer joins. This was also explained, I think, pretty well, but let me show you an example using the data from our car table. If you want to do a join, and you want to find all of your cars who had prior owners, so like all of your used cars, and find out who owned those cars, you would do an inner join. That means it would only find your car record where there was also a prior owner to it. But let's say you wanted to get a complete list of cars, and not only the ones who had prior owners, but the ones who didn't have prior owners. If you do your join on the prior owner field, you would have to do an outer join to make sure that it would get the records where there was no prior owner in that second table. Any questions? I explained everything perfectly. Yes.
The book talked about how there's two different kinds of tables.
The engines?
Yes, so there are two different engines. So the question was there are two different engines or table types that were explained in the book. And I did have to skip a lot because we only had an hour. I think the things that were explained pretty well in the book were the things that I skipped over. So that's MyISM and InnoDB. One of them is good for free text searches, and the other type of table is good for everything else. So I would follow the recommendations. If there are going to be any free text searches, like you want to search for a specific text in email messages, you would want to use the type of table that's good for that. Otherwise, you'd want to use the first type of table that was mentioned. So. Yeah, did they talk about encrypting entire tables, or was it specific fields? Yeah. As the question is about encryption, and yeah, super important. Anything, passwords especially, you would want to make sure that those are encrypted using good encryption, also using the salts. Really follow all the latest security recommendations to make sure that hackers, if they do get access to the database, won't then be able to log in using those accounts. There's a whole lot more to security than that's just that. So I would follow those encryption recommendations. But then also, if you're really doing work where you have to worry about data getting into the wrong hands, make sure you find out all the other things that you need to worry about too when you're writing a secure application. That's pretty important. And don't even try to store credit card numbers, because not only is that something that you really have to encrypt and keep secure, there are PCI compliance requirements, which are really hard to follow if you are storing credit card numbers on your own server. Great. Anything else? Great. Hope I clarified some things for you in the textbook. Thanks for coming. Have a good night. Yep.